Well, when he died, before he died, he made a bequest to the BSCE, and it was to provide funding for education of young hydraulic engineers, loosely interpreted. And so funds from that bequest have gone to provide this annual lecture. In addition, the Freeman Committee gives out some modest educational awards to young engineers. These are not just students, but they can be practitioners working in the public or private sector. And if any of you with the right demographics would be interested in applying for one of these grants, please let somebody from the committee know about that. And in addition, if you have an idea for a future Freeman lecture, we'd be happy to hear about it. They usually take place about this time in April. Usually April is part of spring, but it's it's about this time of year, and we start thinking about it maybe 6 months earlier, the previous October. So please let us know if you have any suggestions, and we'll seriously consider them. So with that, I'd like to introduce another member of the Freeman Committee, Pete Shanahan, who will actually introduce our speaker.
Well, good evening. We're pleased to have a truly distinguished speaker for this year's Freeman Lecture, Dr. John A. Cherry. Dr. Cherry is very well known for his many, many contributions to the science and practice of groundwater. He is Distinguished Professor Emeritus from the University of Waterloo in Ontario, Canada, and currently he's a Adjunct Professor at the University of Guelph, where he directs the University Consortium for Field-Focused Groundwater. And some of you may have recognized this by its old name, the Solvents in Groundwater Research Program. It's a continuation of that program. John holds degrees in geological engineering from the University of Saskatchewan and the University of California at Berkeley, and he received his PhD in hydrology from the University of Illinois. With Alan Fries, he is the co-author of the classic textbook Groundwater, published in 1979. And although it's over 35 years old, it's still an authoritative, comprehensive, definitive reference. The condition of mind speaks to how often I reach up and hook my finger in the binding and pull it off the shelf, and I still do that. I've had to glue the binding on a couple of times. But it's still an excellent reference. And it's actually still used as the textbook for the groundwater hydrology graduate course here. John is also very highly regarded for his fundamental work on the behavior of contaminants in groundwater, and particularly chlorinated organic solvents. Some of you I know were like me in the early 1980s, kind of stumbling around in the dark, trying to figure out how we clean up these sites contaminated by organic chemicals. The Superfund Act was passed by the U.S. Congress in 1980, and it was called Super because $1.6 billion was thought to be lots of money to clean up every hazardous waste site in the country. Well, that didn't turn out as planned. It turned out to be a lot more difficult and complicated to do those cleanups than anybody ever anticipated. John and his research group shed more light on that question than anyone else. They brought real firepower to that problem, and I mean firepower in a literal sense. They had a Canadian Air Force's base, and it had a beautiful sand aquifer, and they had permission to do experiments with chlorinated solvents on that aquifer. And they basically released chlorinated solvents to soil and groundwater and watched what happened. And these were truly elegant experiments. They were well-grounded in theory, very tuned in to what was going on in practice, and then very carefully done in the field. There was just one excellent timely paper after another coming out of that program. I was so intent on making sure I followed everything that came out of that program that I regularly stopped in the library to look at the Canadian Journal of Earth Sciences, just to be sure I didn't miss anything. They tied all that work together. Jim Pankow and others with John tied that work together in the text, Dense Chlorinated Solvents and Other DNAPLs in Groundwater, which was published in '96, and again is a classic reference. John is going to speak tonight about a more recent topic, fracking, and this has been very much in the news. Some of that news has been kind of sensational, and I guess you could even say inflammatory. I've been searching for it, kind of failing to find a good, even-handed, technically solid discussion of that problem. And I'm really looking forward to the talk tonight because I know we're going to get that. Before I turn over the podium, I have to digress with one historical note, though. The last time we invited a Canadian to give the Freeman Lecture was in 1979. We asked Dr. David Schindler to speak on April 1st, 1979. That was the day of the April Fool's Day blizzard in Boston. 2 feet of snow fell, the lecture was canceled, and we held the lecture the following April, a year later. So we're very happy history didn't repeat itself. We're very happy to welcome John here with no snow to give his talk. So please join me in welcoming Dr. John A. Cherry to deliver the 38th John R. Freeman Lecture, Shale Gas Development, a Big Environmental Experiment.
Thanks, Pete, for that kind introduction, and thank you for coming. Bad weather, evening lecture, and all of that, and it's good to see that there is an audience. In my career, I tried to make a point of when I would give lectures, speak on a topic that I know something about, and that would mean that I published on the topic and feel confident in what I'm saying. But now I'm on to another track. Speaking about a topic that I don't feel I know all that much about, and so I should explain how I got into this. In March 2012, I got a phone call from an organization in our capital city inviting me to be chair of the Canadian government's fracking panel, an expert panel. And it didn't seem like a good idea. I didn't know anything about fracking, and I thought I was busy at the time. So I delayed making a decision, and I consulted with my colleagues. And my colleagues concluded that I had no legitimate excuse for turning it down, given my stage of life and all of that, and that I needed to look at it as like jury duty. And I said, yeah, but I don't know anything about the topic. And they said, it doesn't matter. You'll be chair. Chairs of committees don't have to know anything at all. You just have to look wise and basically guide the committee and make sure the report is produced. And then so I went ahead with that. And the committee met, and then I realized, much to my dismay, that only about 30% of the committee knew anything about the topic. The rest of them were just like me. They'd agreed to serve on a committee on a topic that they might have read about in the newspapers. And then shortly after that, I began to get invitations to speak. And I indicated to my colleagues, the shale gas thing is getting really irritated. I'm chair of a panel about which I know little. The panel itself, in fact, knows very little, and now I'm getting invitations to speak. And it was explained to me that this is a very big topic in Canada. Fracking is banned in eastern Canada, and all sorts of things were happening. And it was pointed out to me, well, somebody has to be willing to speak on this topic. I can't go around saying that I don't know anything, and I can't go around saying that a committee with very long resumes doesn't know anything. And therefore that I better step up and start to give talks on it. And I've given many talks, and it's kind of an exploration to see if I know what I'm talking about, and an exploration to get viewpoints, and then every time I give it, I revise it. I was giving a talk like this then about a month ago in Brussels at a big EU meeting to sort out what the Europeans might do in terms of research on this topic. And fracking is banned in almost all European countries now. I mean, and yet they're buying Russian gas, and yet they can't get out their own gas. So it's an amazing environmental political scene, this whole fracking thing. And we're just about ready to start this conference in Brussels and in a big amphitheater, and then all of a sudden there's lots of commotion, and a bunch of people walked down, and they unfurled a banner on the stage and said, "We want to speak." And the banner said, "Ban fracking," which I thought was a little bit amusing because it's basically a ban anyway. But the Europeans handle things different than we do. They kind of expected this, so they said, that's fine. You can speak, but all speakers have a time limit, and your time limit is 10 minutes. And they were kind of shocked, and they really didn't have much to say, but they spoke a little bit. And then he sat down and in fact, didn't fuss for the rest of the meeting. Now, I'm told that at MIT we're safe, but if it was Harvard, it would be different. So shale gas is very global, and maps like this appear all over the place. And this little table down to the left indicates the type of numbers that get onto such lists. And I'm told these numbers mean very little. In Poland was supposed to have massive reserves of shale gas, and when they drilled a few holes, they found, in fact, the reserves are only a small fraction of what was predicted, et cetera, et cetera. And in Canada, our numbers could be wrong by a factor of even 10 and whatnot. But these are estimates, and so there are lots of countries across the world that have prospects for shale gas production. And this is a cross-section through parts of Pennsylvania, so really what's the issue here? And in Pennsylvania really has more shale gas reserves or more production than any other state in the U.S. Who would ever have thought that a northeastern type state would be surpassing Texas and Oklahoma, et cetera, in the production of any petroleum resource? So there's a Marcellus Shale down there at 4,000 feet, and there's a Utica Shale down at 7,000 or 8,000 feet. And almost all of these shale beds that people are fracking in are deeper than about 3,000 feet. 2,000 feet is considered exceptionally shallow. So the gas is there, you just have to get at it. And when you drive along highways and you look at a shale and whatnot, you see that it's weathered and fractured. And basically all sedimentary rock is fractured, and shale is particularly fractured at shallow depths. And if it's fractured, then you have groundwater flow and lots of flushing going on. But when you get deeper, such at depths below 2,000 or 3,000 or 4,000 feet, then the fractures are still there, but they're closed, and the shale has locked in the gas. The shale beds are the source of petroleum in the first place in most cases. So the fractures are there, but they're closed, and you just have to get the gas out. And you get the gas out with this amazing technology developed kind of 20 years ago and really got roaring about 10 or 12 years ago, where you drill down and know exactly where you're drilling because you've got directional tools, and then you start slanting your hole, and then you drill horizontally along your shale bed, because in most areas your shale beds, all your rocks are kind of horizontal. And so you drill horizontally along the shale bed, and then you have to shatter the shale. So what is shale gas development all about? Really, it's about shattering the shale so that the gas will then release itself under its own physiochemical state and run up the well. And each time you shatter, then you make a whole bunch of fractures, and you do it a number of times. And shale gas development occurs on a pad. So engineers build a pad, and they make it level, and they put some liners under it, and a pad then is a few acres in area. And then each pad these days has anywhere between 10 and 20 wells drilled from it. So you drill down horizontally in one direction, and you just keep drilling in a radial pattern, because where you haven't shattered the shale is where you're not going to get your gas from. So you have to shatter the whole thing. And that's what separates this type of oil and gas development from others. And this is a science writer's version of the world. Fracking operations typically require up to 18,000 horsepower and sometimes more to pump 18,000 barrels of water with chemicals and between 165 tons of rock, crack openers, sand, or proppants, as many as 40 times to create fractures along the lateral well. So you got your lateral well going out in the shale, and you basically do your shattering operation, say, 40 different times. And then I haven't visited a pad in operation, so I haven't seen any of this stuff, but I've talked to a lot of people who've been there. And recently I talked to an engineer who makes his living going in and figuring out how you seal a well that's gone bad. And this is kind of his description of what happens on a pad. Like, it's organized chaos on each pad, but it's well organized enough with enough engineering so you complete your well and you get gas out of it. Otherwise it would be a failure. But there basically can be more than 100 people there, and all sorts of fuel and engines and whatnot and so forth. So it's a phenomenally amazing technology. And these aren't from the same two sites, but on the left we see a pad that's in operation. And on the right we see what the countryside looks like after you're done. So the thing about shale gas development is it's a lot of disturbance in your neighborhood if you live nearby, But the disturbance only lasts somewhere between, say, 3 and 12 months. So it's a highly chemical intensive, energy intensive, noisy operation, but it isn't there forever. Now, when it comes to a township or a county and whatnot, then you will have dozens of pads. So for a period of time, then basically your neighborhood and your landscape and your whole rural way of life then it takes on a great change. And this is what it looks like from Google Earth. So the end result of all this, without any land or land reclamation, which doesn't happen, is basically a pocked landscape. And each pad has pipes to it, it's got a well to it, it's got ditches and drains and all that stuff. So basically, shale gas development is very different than your normal oil and gas development in the intensity of activity on the landscape. So the public are excited over this all across the globe in a way that's quite astounding. It goes beyond the anti-nuclear demonstrations of the 60s and of the 70s, et cetera. And it's caught basically government and industry and academics and everybody by surprise. And look at this. A few days after Chevron obtained their first building permit, Pogesti erupted in revolt. 3 days of clashes between locals, activists, and riot police followed. Wow, like what's this all about? So in the United States, and the US is the heartland, of course, of shale gas development, and it's brought great things to your economy. And I'm told then that 24 states have involvement in shale gas development. Now I think some of those states aren't doing actually the shale gas production, they're producing the sand. So in fact, sand mining became such a big deal in Minnesota recently, it got so out of hand because the regulations weren't there to control it, that the state of Minnesota has banned a new sand fracking mines. And the fracking industry knows the type of sand that they like, and you go in this world with what you know works, and it's a particular type of rounded sand that does an amazingly good job. I'm told that we have such sand in Canada, but it's not being mined and it's not being used, because why would you go to a new type of sand that's a little bit different and then risk failure when you can buy it from the US? Now, in the US, the only area that really is strongly anti-fracking is New York State, and that's likely got to do with the socioeconomic bracket of the people who live in the areas where the shale gas reserves exist. But in Canada, it's a very different story. We've got shale gas reserves in the north, up where we have our Aboriginal people living mostly. It's being developed very highly in British Columbia. That's depending upon it as their economic engine driver. And in eastern Canada, we've got reserves in Quebec, Nova Scotia, New Brunswick, and Newfoundland. And in those areas, then, they're either bans or moratoria. And you all know that we Canadians are very peaceful people, and the only thing that brings us to violence is hockey. But as I'll mention in a moment, shale gas is now the second thing that brings violence to Canadians. So in eastern Canada then, the reserves are where people live. So for example, there are large reserves between Quebec City and Montreal, and there are 2 million people that live in that area. So it's no wonder they're taking a different viewpoint than say you would if you lived in Vancouver and you can have your fracking going on up in the north. And there have even been outbreaks of violence in New Brunswick. Police cars burned and all of that. Nobody hurt, but it certainly is a show that has made everybody think about the future. And in these parts of the world, whether it's Europe or Canada, where fracking has been banned, not only has fracking been banned, but in fact you can't even go out and drill holes to find out if you have any shale gas to develop, because people can't tell the difference between going out and drilling to find out what the reserves are and whatnot. So governments can't even get in a position of finding out if there are reserves there that they maybe could use in the future, et cetera. France was one of the earlier countries. They just banned everything back in 2011 in France, knowing that the French farmers would probably roll their tractors out on the highways as they're prone to do in France. And so that was the end of it for the French government moving in that direction. So when I gave my first talk on this topic, just a few months after I got onto this panel, I gave it in New Brunswick, and outside there were protesters all over the place, and this is one of the photographs we could take at that meeting. Wow, social license, like what's that all about? So in the new form of democracy, we vote our politicians in, And then our politicians will want to develop something or other, but in fact, then you have to have a social license. And there's an empowerment there that's going on that kind of changes the nature of our democracy. Quebec is the only jurisdiction I know of in the world that actually where the government behaved in what I would say is a responsible way. 4 or 5 years ago, the Quebec government realized that there could be violence, and they basically put millions and millions of dollars into scientific studies. So just about every academic in the province of Quebec that would take an interest in the subject was funded to study something or other. Now, they couldn't study fracking because fracking wasn't going on, but they could study the groundwater, and they could read the literature, and they could run their models, and they could basically become educated as a society. So there's no difficulty gathering a group of scientists and engineers together in the province of Quebec and having a meeting where people are relatively well informed because they've had research grants and grad students working on it, et cetera. Now, before all this happened, there were 30 wells drilled in the province of Quebec, so they know something about the reserves. And after the fact then, when they went back to these wells, they all leaked stray gas, which is really the issue that I'm getting here in a moment. So where are we at? So fracking is happening in many US states, and it's also happening in Alberta and BC. It's in the early stages in Argentina, where they're drilling lots of holes to find out how much shale gas they've got, and in China and in the UK. Now, the UK was very anxious to get going on fracking a number of years ago, and they haven't been able to do it because of public outcry. And finally, the British government said, well, we're going to do no fracking on public lands. We're only going to do it in basically national parks. And that even got the people more outraged. And so what the British government has decided to do now basically is put basically tens of millions of dollars into research. And it's hard to do research fast, and it's hard to do research on fracking when you're not fracking. But anyway, that should have been done a decade ago. And it's not happening then in New York, Quebec, New Brunswick, Nova Scotia, and Scotland, et cetera. So why is the United States so different? Why are you the leaders on this by far? And one major reason is the money is the driver. So in the US, as opposed to most of the rest of the world, as opposed to all the rest of the world, the landowner in many cases owns the mineral rights. So when fracking comes to your community, there's money going into people who own the mineral rights, and also the way your system works, there's money going into the local community. So basically there's a money flow into the local environment where it's happening. In Canada, there's no guaranteed money flow. So if you're sitting out there in rural Quebec, your government's going to say, we need to get ahead with fracking here, and it's going to be good for the national good or the provincial good. The question is, well, will it do your community any good? And it's your community where the disturbance is coming. So as I mentioned, I was appointed to be chair of a 16-person panel, an excellent panel with people with long resumes and in 12 different disciplines. And it's in my entire academic career, I don't think I've ever been in a room with a sociologist before. And a bunch of other disciplines, given the cloistered environment that some of us operate in. So it was a really wonderful intellectual experience. The panel was all academics, and that's the policy of this organization, no people from industry, et cetera. And there were 4 Americans then and 12 Canadians. And I guess in keeping with what we'd expect, the Americans were highly polarized, and 2 of the 4 resigned before the end of the panel. But that was good. The polarization actually led to really active debate, and it certainly caused me to have to get up to speed in a hurry, realizing the fury around the topic. Now, it was fortunate that our panel got going late in the game. So before we got going, there had been at least 6 other panels. And that was very comforting. At least we could read what other groups of experts had said when they sat down with the same problem. And all these other panels were the same as our panel. They basically knew almost nothing about the panel. And the German panel was specifically chosen to have nobody who knew anything about the topic, so they could start off fresh without bias. So all we had to do was look through all the concerns of all the other panels and then look at the recent literature and have our own debate and make our own recommendations. Now, there's a correlation with panel recommendations. If you have groundwater people on a panel, of course, you're going to have quite a bit of attention focused on groundwater. If you have health experts on the panel, you'll have health comments. Many panels had basically hardly any groundwater experts, and most panels had no health experts, no toxicologists. Some of them had no ecologists. And so our panel was relatively broadly based and missed only, I would say, one expert that I'd wish we had, which would have been an energy economics, energy policy expert, because at the end of the day, that's where it all boils out. There are lots of concerns, and a concern doesn't mean that there's a problem. A concern, it just means it's a topic then that deserves looking into because people have some reason for concern. And I'll, of course, focus on the groundwater part of this. Now, if I'd read this article before I took on the job being chair of the panel, I probably wouldn't have been chair of the panel. I didn't realize there were so many big issues here to debate, and the Scientific American really did a good job. They interviewed all the appropriate players at that time and got a whole variety of points of view. And the title of this talk then really got on my mind long ago, being taken from Amy Moll, and I don't know her, but this is her statement as I've quoted from the Scientific American article. And so in terms of groundwater, what is there to be concerned about? Well, there are impoundments and there are storage facilities for fracking chemicals and fuel, and there are pipelines and transportation, etc. So there are certain possibilities or probabilities that there are going to be leaks from these surface activities. Keeping in mind that a pad only functions between 3 and 12 months, so these probabilities are there at a particular pad only for a relatively short period of time. But this is, I would say, small. This isn't really the heart of any significant issue. If governments want to minimize the possibilities of these things, they can pass regulations and whatnot and deal with it, and that the science is reasonably well known. Now, we don't know what the fracking chemicals are, and we don't know how the fracking chemicals are going to interact and all of that stuff, but that's more, I think, of a health issue and worker safety and whatnot than related to this diagram. So the big issues and the big uncertainties are when you go deeper. So the question is, well, what's going to leak up and get into groundwater from below? So it's threats from below that are the big uncertainty. And a lot of attention has been paid to the fracking chemicals. And governments and industry made the big mistake of not divulging what these fracking chemicals are long ago. Okay, that should have been a no-brainer. So people think that a big victory will be had if legislation is passed so that the fracking chemicals are divulged. Like, as a groundwater scientist, what would I do if you give me a list of 100 chemicals I haven't heard of before? Okay, that's not going to do me any good at all. What you had to do was do lab tests and whatnot to indicate how do they interact, and how would they behave. I mean, a pesticide company doesn't get the license of pesticide by just giving you the chemical formula of the pesticide. Okay, they have to do all sorts of tests to show how it'll behave in the environment. So the fracking chemicals disclosure thing is kind of it's a high-profile semi-red herring. Now, so one of the big concerns has been, will this cocktail of chemicals that we don't know anything about, but which people fear, somehow get up into the freshwater environment from the fracking zone? Okay, and the fracking zone is down below 2,000 or 3,000 feet, et cetera, and I've indicated those here in yellow. And for a whole variety of reasons, that's a highly unlikely event. But it's been a great red herring. And here's a person who writes a book on whatever the going issue is in Canada, and he's, I think, a political scientist, but he gets a whole page in one of our national newspapers on this topic. And no scientist even gets a 200-word column, scientist or engineer. So the Environmental Protection Agency have no proven cases of fracking-related contamination, exactly zero, not a single one, and anywhere, et cetera. And what is meant by this, there's been no indication that fracking chemicals have come up from the fracking zone. Well, the people who study the physics of this say it's not going to happen anyway. So this is really is a non-finding and is very misleading. And this is just another way of pointing out the same thing. And there are a variety of papers on this in the peer-reviewed literature, and my colleagues have explained this to me on many occasions who understand it. And the last thing we need to worry about is whether or not then fracking causes these chemicals and brine to get all the way up from the fracking zone. So that raises the question, well, what is the concern here? So the concern is stray gas. So these wells have lots of casing. So you have a surface casing, you have a conductor casing, and then you've got surface casing, and then you've got your intermediate casing. And after 3 casings, you have your casing that's going to get you down into the fracking zone. Okay, and all these casings then are sealed with cement. Okay, and that's the heart of the issue. Now, the British report done by the Royal Society of Britain then made this statement: ensuring well integrity must remain the highest priority to prevent contamination. And that sounds good, except there's no advice on how to ensure it. And there was no indication in the British report what the problem is anyway. But people realize that making wells that don't leak is important. The German report went further, and they brought out into the open something that's laying beneath the knowledge base for a long time. The industry's 8 decades of experience with the long-term stability of cement shows that gas well cementing does not remain leak-proof indefinitely. Okay, so basically cement is unstable in those geochemical environments, and you can expect your cement to deteriorate, and therefore you can, one way or another, expect that all wells will eventually leak in some way. Now, the fracking community would explain, and we had great debates in our panel. Our panel was charged with the task of figuring out what would be the environmental impacts of fracking over and above any impacts of the oil and gas industry doing what they always do. So we weren't charged really to figure out what fracking would do, except for the fracking part. But we ignored all of that, and our mandate was relatively broad. So when you dig back in the literature, then you find statements like this. And Carlos Mullenbach is the distinguished isotope geochemist at the University of Alberta, and he's been working away for a long time with hardly any funding, kind of looking at what he sees in the way of isotopes with the fluids coming out of oil and gas wells. In a large number of conventional wells, vertical migration of gas from unknown sources to the surface via well casings and surrounding soils represents a serious environmental problem. Now, he's at the University of Alberta, in the province of Alberta, and any statements like this made in Alberta generally get thoroughly ignored, and he's been shunned for a long time. But then there was another paper out there, when you start to look at things, by my good colleague from the University of Waterloo, Maurice Dussault, who speaks on this topic globally and is a geomechanist of the highest renown. And he wrote this paper in 2000. So when I began to talk to Maurice about this, I said, John, what about this shale gas issue? He said, well, you read my paper. Nobody read it back when I published it. It was just stone silence. And so this paper now has become highly cited, after basically more than a decade in the silent wilderness. Oil and gas wells can develop gas leaks along the casing years after production has ceased, and the well has been plugged and abandoned. In North America, there are tens of thousands of abandoned inactive or active oil and gas wells that currently leak to the surface. Okay, this has nothing to do with fracking. It's just got to do with the oil and gas industry. Standard practice. Current standards for oil well cementing are either not well-founded or based on a flawed view. And there's no denying this. Nobody denies it. Nobody says that this is out of date. This is now widely accepted. And here's some more quotes from Maurice and colleagues. Thousands of wellbores, and this is more recent. They've really been digging into the literature on this to try and find out what is the Canadian record. Thousands of wellbores are leaking methane, including 27,000 leakage reports in Alberta since 1971. About 10% of all active suspended gas wells in British Columbia, and about 20% of all energy wells in Saskatchewan. Okay, so that's reasonable. I mean, cement, even if you do the cementing job proper in the first place, doesn't mean it's going to last over a period of years or decades. So what is this all about? Well, if you look on the left here, that's a slice through a cemented casing annulus, and you can see those little cracks. So if you're lucky enough to get the cement totally filling the annulus after you cement your well, then you have to get through all the fracking activity and all of that vibration, etc., and hope that you haven't got your cement cracked. And on the right, then, we have an example of an annulus which hasn't had cement squeezed into all the openings. So a well with perfect integrity is a well where you've got your cement entirely into the annulus everywhere, and that you haven't damaged it through all your subsequent activity, and it hasn't yet deteriorated. And so when I began to talk to people in industry on this, and I thought they were going to, call me an environmentalist or whatever, they basically said, yeah, we know all about this. This is a big challenge. And Shale in particular has been very interested in this challenge and showed up at one of our meetings we held in Alberta that I'd organized on this topic, and basically gave us a lot of information about, in fact, wells that they had sealed with their best technologies of the day in northern British Columbia, and yet the cement integrity was not up to their desired standards. So it's a very difficult challenge. And the challenge is so difficult that one of my good colleagues, Richard Jackson, who publishes in the peer-reviewed literature, and along with Maurice Dussault, I would say are maybe the most knowledgeable people in the world on this topic, having dug into the records, Dick says, creating a good cement seal is one of the most difficult engineering endeavors that I know of. Now, when you read the propaganda on this topic, you'll read, yeah, you're going to do a good cement job, and then after you do your cementing, you're going to do a bond log. And a bond log is a geophysical tool that you lower down the hole, and it purports to tell you whether or not you've got your analyst fully sealed with cement or not. Okay, well, the bond logs used are relatively old technology. The bond logs that are high technology generally aren't used because they cost more money. And when you talk to bond log people and you say, what can you see and what can't you see in the size of the analyst, in fact, they can't quantify it. So when you drill down then to your shale bed, which is quite deep, you have to drill through a whole bunch of other beds. So what is this leaky well problem? So you're drilling down through the other beds, and lots of other beds in these petroleum-rich provinces then are charged with gas. Okay, so we have the freshwater zone, which is what we're concerned about. We have the intermediate zone, which is all these beds that are above the shale gas zone. And then we've got the deep zone, which is where the petroleum industry knows a lot. But the zone in between, the intermediate zone, is a zone really of minimal knowledge. The oil industry drills through it as fast as they can because there's nothing to be gained by studying it. The hydrogeologic community, as soon as we get into brinish water, then brackish water, we lose interest. So the intermediate zone really is a zone of great scientific uncertainty and lack of knowledge. So what is the guts of the problem? The guts of the problem is when you drill any oil and gas well and you drill down, you're puncturing gas-rich zones almost invariably, where the gas has been locked in there for millions of years. And then you keep on going down to your petroleum resource to develop it. And so the challenge then is you have to seal all those casings and the annuli, et cetera. You have to get them sealed so all the gas-rich zones that you punctured don't leak. And this leakage is called stray gas. And so stray gas then is the culprit. So what do we know about stray gas impacts on groundwater? And the answer is, well, not much. Although thousands upon thousands of wells have been sampled, in Pennsylvania and Oklahoma and Texas, et cetera. But what do people sample when they go out to sample? They sample domestic wells. And a typical domestic well in Pennsylvania looks something like that. And it's basically probably the worst scientific instrument you'd want to sample if you're in the business of trying to get reproducible data. So you go to the homeowner and you sample it once, and the results you can get can depend on the day of the week and where their pump is and how much water they pumped before, et cetera, et cetera. And many of these wells leak from the surface too because their cement casings have deteriorated. So why does the oil and gas industry and why does government basically have regulations causing all these domestic wells to be sampled? And it's basically about liability. So these investigations aren't scientific investigations, they're liability investigations, and they don't tell us very much. People like me and my colleagues would argue about what's happening scientifically. Now, but there's some bombshell science that's coming out of this that's published in the peer-reviewed literature, and if it's not published in the peer-reviewed literature, then it's not worth reading in general. If it's published in the peer-reviewed literature, at least that's honorable publishing, and it means you can write a note on it, and that people have worked hard to make it understandable and legitimate. So this is from what I'll call the Duke University group, and there's the Duke University group, and there's a Texas group, and there's a Syracuse group, et cetera, and they're all fighting it out in the peer-reviewed literature on whether or not, when you go out and sample domestic wells out in the countryside, whatever it might be, whether you're seeing the effects of stray gas that you can attribute to fracking. And so overall, our data suggests that some homeowners living within a kilometer from gas wells have drinking water contaminated with stray gas. And they go on to point out that this stray gas then has to be related to the fracking, to the shale gas development, not the fracking, but the drilling of the well for the fracking, et cetera. And this group publishes a paper about every 6 months, and I'll get to that in a moment. And so this would be a scenario. So this would be a scenario that people like me would draw from their data, whereby the thin gas zone comes up the leaky wellbore and produces a gas plume. And sometimes when I present this, my colleagues say, John, you've got to stop showing this diagram because there's no basis for it in science. You can't go around saying that gas disperses that strongly. And my argument is, I'm going to keep presenting this diagram because, if somebody wants to draw a different one, that's fine. But you have to draw some sort of diagram like this if you believe the results that the Duke group are producing. I'm not sure I believe those results, but in fact, those are hypotheses that are on the table. So when the Duke group publishes, usually within 6 months or a year, somebody else publishes either a rebuttal or goes out to another part of the US and samples domestic wells and gets a different answer. And so this is all unreproducible science. Okay, it's unreproducible science because you can't go back to the same area in Pennsylvania and sample the same wells because the wells are secret. Because when you sign up with homeowners to sample their wells, the deal is you're not going to tell anybody about the quality of their well because that can decrease their land values, et cetera. So all this sampling of rural wells that goes on, it doesn't matter which north of the border or the south of the border, then isn't reproducible science because of the nature of the beast. Now, people like me would say, well, why don't you go in and you spend a few $1 million putting in monitoring wells and on and so forth. Okay, that's what no organization has yet done. And until we get there, we're not going to be making much progress. So all we have in the literature then is this great debate that will never be resolved. And each additional paper has an additional suite of isotopes. So every isotope and every noble gas under the sun that any geochemist could ever think about producing on any machine anywhere has actually been used to analyze these water samples. Now, there's this famous graph in the upper left, and if any of you have watched the movie Gasland or Gasland 2, if you want to watch a movie on this that's interesting, watch Gasland 2. It's a scientific movie, not like Gasland 1, with lots of interesting interviews, etc. But it's got this famous graph by Schlumberger that basically shows the percentage of wells in a particular area, and I don't know the area, that leak after a period of 2 or 3 decades, etc. So I think it's safe to say that all wells can eventually leak, at some level. But under what circumstances will the leakage cause substantial harm to groundwater? Really, that's the issue, and that's not the debate then that's being held or that's being researched very much. So we drew up this diagram just so we'd have something to show here. So when the methane starts to leak and gets off into the freshwater zone, methane can be a hazard in its own right if it builds up in basements and whatnot and so forth and causes explosions or causes people's taps to light on fire and all the things that you may have seen in the Gasland movies. But those are relatively unlikely scenarios. The more likely scenarios, the methane goes in the aquifer and a bunch of geochemical reactions are stimulated because methane is food for bacteria, et cetera. And when you start to then write some little equations here, you can change the pH and you can change the EH, and all of that can change the water chemistry. So the issue really is, if stray gas is a contaminant and gets into aquifers, then what are the chemical reactions that it's going to unleash? And most of these equations lead you then to a conclusion that the water quality is going to deteriorate. It doesn't mean it's going to kill you. It just means that your water quality is going to deteriorate, and you're probably not going to want to use it, and you're probably going to blame the government then for having changed your water quality, all of which is reasonable. So, so governments are grappling with this, and governments basically, wherever they are, they're desperate to get on with shale gas development because it leads to money and lower energy prices and jobs and all of that. So then the question is, what do you tell people out in the countryside, around Quebec or Nova Scotia, New Brunswick or wherever, what should the separation distance be between a fracking pad and a domestic well? And that's where all sorts of nonsense gets produced. Like a Canadian number is 200 meters, and it's 200 meters because we're operating in meters. The American number is whatever it is, 500 feet, et cetera. None of these numbers have any bounding in science whatsoever. There's not a single calculation you can make on the back of an envelope that would lead you to believe that any of these numbers have any grounding on anything. 200 meters would be too close. 2,000 meters would be too far because then you couldn't develop the resource. So if you believe then that stray gas is not going to be a problem, and you're free to believe that. You can believe anything you want in this topic because there's so little science. But if you want to believe that stray gas isn't going to be a problem, then what are you believing in? And it seems to me you have to believe that there's an adequate assimilation capacity. Okay, so like what's the assimilation capacity for a bit of leaking methane into whatever your aquifer is, et cetera? And assimilation capacity is an old-fashioned term that I think I learned when I was a grad student at the University of Illinois and took my first course in water quality that had 3 weeks in groundwater contamination in it, where I learned about the groundwater transport equation. And back in that era then, we learned that really the assimilation capacity is the basis for a modern society. Okay, we emit vapors into the atmosphere, we discharge things into rivers and lakes, and if we couldn't do these discharges, we couldn't function. So assimilation capacity is basically part of our modern civilization, and it applies to tens of millions of Americans and Canadians who flush their toilet if they have a septic system. So if you have a septic system and whatnot, you're believing that somebody knows something about the assimilation capacity and you're not doing the environment harm. Now the purpose of a septic system is to treat the organic matter and to convert the ammonium to nitrate. So from a groundwater viewpoint, the purpose of a septic system basically is to produce a nitrate plume. And if you're not producing a nitrate plume, then your septic system isn't functioning properly. Then it's not converting the ammonium and whatnot to nitrate. So if you don't have too many septic systems and you have a good assimilation capacity, relatively speaking, then you're okay. And I borrowed these slides from Dennis LeBlanc. We were at the same meeting a week and a half ago, and they're excellent examples. So probably one of the leading areas in the world where the assimilation capacity for septic systems has been exceeded is Cape Cod. And there's nitrate all over the place, and it's very important because it causes the ecological environment in the estuaries to suffer greatly. Etc. So if there was a much lower density of septic systems, then you wouldn't have these problems. So this is an example of people proceeding in a modern society based on the assimilation capacity concept, but not really using it, not really tracking it, ending up with a problem. Now what's even more amazing these days, when you go out and sample groundwater for very sophisticated things like pharmaceuticals and food sweeteners, we're now finding them all over the place, as they have on Cape Cod, as we do around Guelph and Waterloo, etc. So the simple human act of putting things into a septic system is leading to kind of amazing things showing up in groundwater because we didn't get the quantification right, and we didn't think it through, and we didn't ask the right questions. Now, when in doubt, in the world that I've operated in, and we're wondering how a contaminant behaves, or if we have a problem on our hands that we want to test, we go out to our Borden aquifer and we pump it into the aquifer, whatever it might be, whether it's Dean apples or benzene, et cetera, et cetera. And a lot of science, as Pete mentioned, has come out of this. And what we learned back then in the 80s when we began to do this, much to our great amazement, was that hydrodynamic dispersion was orders of magnitude smaller than we thought. So if you read the Freeze and Cherry book that's made me so famous, when you read things about dispersion in there, it's nothing more than nonsense. It's nonsense because the parameter values are all wrong by orders of magnitude. And that has big implications for assimilation capacity and a whole bunch of things. But I guess the reason I'm mentioning it here is it's interesting in the evolution of scientific knowledge how for a period of time we think we understand something. So up until we did these experiments, we thought we understood hydrodynamic dispersion. The equations were all there. Now the equations were unfounded and the differential equations were solved properly. It's just that the conceptual model on which the equations were based just wasn't quite right. And then somebody comes along and things aren't adding up all that well, so we actually do some experiments, and you find out then that your whole foundation for thought on the topic was wrong. And I mentioned this then because what we have in this whole shale gas debate is a lot of people who have opinions, and it's kind of interesting to know whether the opinions are based on kind of professional judgment and bias and whatnot and so forth, or whether they're grounded in science. And then the USGS did a big experiment like this. And you say, wow, experiments like this? This is an expensive experiment. It was all done to understand what we thought was a real simple process. And that's hydrodynamic dispersion for a slug source in a relatively homogeneous aquifer. And when you start upping the ante and you put some more geological complexity on it, okay, then it really gets complicated and our ability to model it becomes worse and worse. Oh, so the German panel then, and almost all these panels recommended research. Scientists should set in motion far-reaching and long-term basic research aimed at gaining greater insight into the procedures and processes entailed by the use of unconventional energy resources. Now, Germany is in a process of banning shale gas development, and in a way, scientifically, that's too bad, because in fact, their recommendation of this panel was that Germany should go ahead with very limited and cautious shale gas development in one part of Germany where the environment looked to be as safe as possible. And basically, the view was that large funds should be poured into research at those fracking pads, and that the early fracking work in Germany should be basically viewed as a large scientific experiment. And so when I saw that, I said, well, maybe there's at least one rational country in this world that's going to do that. But unfortunately, the Germans are banning shale gas development, and so they're not going to do these experiments that the rest of us should be doing, but are not yet doing. So there's hardly any research on this topic, which is mind-boggling, because it can cost $1 or $2 million to just do one frac well. Okay, and then you have 10 or 20 wells per pad, and then you got a dozen pads per township. So very quickly, in any real little local area, you're up to billions of dollars. Up to billions of dollars, and yet there's not a single pad that has had any rigorous groundwater monitoring that I know of anywhere in the world. So research is just beginning, but there are no plans yet that I know of for truly substantial groundwater impacts research. And I'll just give you a couple of examples of research that is fun, and it'll be relevant, but I don't put it in the world of substantial. So what do Canadians do when they're wondering about how a new chemical behaves? We go out to the Borden Aquifer, we inject some in the aquifer. Okay, and that's what we're doing. So we're going to inject our methane in and see if we can predict what happens. And there are very powerful models that allow you to simulate transport and dispersion and chemical reactions, et cetera, and we'll use those. So this is an exploration in the starting points of assimilation capacity understanding, et cetera. And in the province of Alberta, with federal government money, there is some substantial money about to be spent on a field research station. And this is a square mile of land out on the Bald Prairie east of Calgary, which the University of Calgary, with federal funding, is going to turn into a field research station for research groups from all over to do stuff, just like the Borden Aquifer served as that. Now, it's not a real fracking pad, it'll never been, so it's not threatening. Okay, it's an experimental site, so it's not threatening to any particular company or any particular government. But it's substantial. So we're going to drill down to 300 meters, 900 feet, and we're going to inject methane and CO2 because CO2 storage is an issue too. And then one of the experiments is going to be at 1,500 feet. And then if the money holds out, we're going to monitor just about everything that's one can monitor with every type of tool that we can find, basically in the upper 1,500 meters. So it's an exploration in understanding the intermediate zone that's just getting going. They just drilled the first hole, and it's a methane-rich environment, and we're gonna establish a domestic well and whatnot and so forth. So the scenario for stray gas plumes, the gas migrates upward, but it's got to migrate upwards through pathways. And nobody in the literature has analyzed, or that I know of, how big these pathways may be. And of course, the gas is the issue because it's buoyant and it can come up as bubbly flow or slug flow or whatever. Okay, that seems reasonable, and the physics of that is reasonably well understood, I'm told. And so the issue is, well, how big do the openings have to be? And in another context that also involves multi-phase flow, back in the 90s, we worried about that. And we went out to a site with a nice clay deposit with some little fractures in it. And we took it to the lab at Waterloo. And we put it in a big triaxial cell, and we reestablished the stress conditions so that this chunk of fractured clay would be as reestablished as possible. And then we ran DNAPL through it. And eventually, after a week or two, DNAPL dribbled out. And what we found then was a chunk of clay that was so tight, the fractures were so tight, that you couldn't really show with a hydraulic measurement using water that it had fractures. It did a fine job of passing DNAPL. And then you start back calculating these apertures. And of course, an aperture is a figment of anyone's imagination, but we have to actually have them for our models, et cetera. And depending upon how you calculate the aperture with that experiment and others, you get some small numbers. Now, the average diameter of a human hair is 100 microns, I'm told. So we're talking about apertures that are truly significant for DNAPL migration that go down to 1/10 of the diameter of a human hair. So if there's anything like this that relates to stray gas movement, then we're talking about pathways that could do a lot of transport and dispersion. Now, monitoring. And so all the expert panel reports you look at recommend there should be monitoring, but there's no advice on how to do it. And the only jurisdiction anywhere in the world that's about to pass some regulations that require monitoring is California. So California has a panel that's going to make some recommendations because they have a drought and they are serious about their water supplies. And I'm on that panel, and it'll be interesting to see what comes out of California by way of special monitoring regulations and whatnot, specific to hydraulic, they don't call it fracking there because they don't do much horizontal fracking, so it's fracking vertical wells and everything's different. Now, the government of Alberta has been agonizing over whether they should actually start a world-class monitoring or not. And in Alberta, they bandy around this term world-class a lot. That's because they don't have the slightest idea what it means. But they had a very good panel, independent panel, making recommendations on basically, how would you go about monitoring? And one of their recommendations is, and the province of Alberta might actually do this, would be to set up a monitoring organization that's truly arm's length from government and that has scientific review at a high level. So in fact, it might be a type of monitoring that the public could trust. Now, they haven't done it yet. 5 years have gone by. They're working their way down the road, and it's pretty scary, I'm sure. So some of us who like to get into groundwater monitoring can envision monitoring at a pad where you drill a bunch of holes and you've got a bunch of multi-level monitoring devices down to 1,000 or 2,000 feet, and you monitor it intensely to see what you see. And one of the arguments against this that people make is, we don't think you're going to see anything. So why would we spend a bunch of money if we think you're not going to see anything? And our argument, that's great. If that's what you think, you'd better prove it. And this is what we think the Germans would have done if they were going to head down that road, and which hasn't been done and isn't planned yet, as far as we know, for any site, any pad in North America. Now, low on the list then of concerns that when we listed them was earthquakes, and it's a very amazing story that I'll tell you that's fast developing. So here's a statement from one of our science writers in Canada. For years, industry and fracking experts argued that technology wouldn't cause quakes that could be felt at the surface. Okay, now you've read a lot about earthquakes caused by the shale gas development industry, but that's through basically waste fluid reinjection. Okay, those are injection wells, and we all know that if you overload an injection well, you're going to have earthquakes, et cetera. So that's not the issue here. The issue here is whether fracking itself is going to trigger earthquakes that matter. And here's what we wrote in our expert panel report. And as chair of this report, I'm kind of responsible, more or less. And when I read this chapter and I saw this sentence, and it was right late in the game, and I don't know exactly who wrote it, but I let it go by. The science of how fluid injection can cause seismic events is well understood, and the risk can be minimized by being proactive. And whenever you see that statement being as well understood, it means that somebody has an equation and they believe the parameters in the equation, as near as I can tell. So I worried about this statement, and I looked around to find people that I think could look at it from a very high level, etc. And I found Dr. Emily Brodsky, that I've gotten to know at the University of California. And I'll let you read, and I just sent this to Emily a couple of months ago. I said, Emily, we wrote this sentence in the fracking report, and what do you think of it? And here's her response. So, and then recently she's in Europe on sabbatical, and she went to a big conference in Switzerland, apparently a few weeks ago, where a room with 100 people of seismic experts debated about what they know about seismicity in a context of shale gas development. And so this statement up above is an example of how expert panels can make statements that in fact are wrong and misleading if they're not paying attention to all of the details. So something big has happened in Alberta, of all places. So an earthquake of 4.4. Now that's not enough to cause a building to fall down. I mean, people jump out of bed and they stub their toes and whatnot, but 4.4 is getting up there. But the historic part of this earthquake is it's definitely attributable to hydraulic fracturing. It's not attributed to waste disposal injection. So that sent this reporter, one of our outstanding science writers in Canada, Andrew Nikiforuk, on a quest to find out people who know about this topic. And they found this professor, that I also don't know her, at the University of Western Ontario, but she's a well-respected expert. And here are a couple of her statements. Earthquakes induced by fracking can produce more damaging ground motion at lower magnitudes than natural quakes due to their shallowness. Earthquakes triggered by fracking could possibly cause damaging ground motions at magnitudes as low as 3.5 to 4 due to their shallowness. And what I learned when I went to the conference in Brussels a month ago from a Dutch geomechanicist, he said, well, there are parts of Holland where where gas production, not fracking, where gas production has been causing earthquakes. And in fact, the Dutch government has just basically provided $2 billion to homeowners to compensate them for reduced property values. Okay. Nothing damaged, it's just the property values are going down because people are living in fear of earthquakes. And so the whole topic of earthquakes in a fracking context now is opened up for debate and concern. So one of the big problems is that there's almost no science informing policy in terms of shale gas development. Shale gas development got going fast, it got going without research, it got going without anything in general that we regard as rigorous regulations, etc. And Dr. Naomi Oreskes, here now at Harvard, who writes books related to climate change, etc. Here's a quote from one of her well-known papers. At best, science produces a robust consensus based on a process of inquiry that allows for continuous scrutiny, re-examination, revision. So if science is going to inform policy, then we have to get to the point where we've got some sort of consensus in the scientific community. And based on what I've read, I have this chart here. Almost everything you read is either propaganda, junk science, or dishonorable nonsense. Now, honorable nonsense is a special category. Honorable nonsense is a paper published in a peer-reviewed journal that just happens to be all wrong. But I regard it as honorable because it's published in a peer-reviewed journal. And in fact, there were one or two papers on that topic recently published on modeling fracking fluids that basically set off a really good, healthy debate in the peer-reviewed literature. Now, you can blame the peer review process for allowing honorable nonsense to get published, but it happens in science and it shouldn't be discouraged. We've got a lot of immature science. Unreproducible science is all that work sampling domestic wells by our isotope experts. Very good, very sophisticated work and whatnot, but it's unreproducible science. And then we've got immature science, and then we've got mature science, and we hardly have any, and I don't really know of any mature science on this topic. So the state of the science in nearly all shale gas issues is immature. Nearly all questions are being widely debated in the scientific community. Anthony Ingrafia is a renowned professor at Cornell University, and he's been speaking on this issue at many conferences. And so we are conducting a large-scale experiment on the environment and human health. So he's just saying the same thing that Amy Mall did. So what is the experiment? Well, scientifically, and if keeping human health out of this and all that stuff, the experiment is gas-charged beds in the intermediate zone are being punctured in an unprecedented frequency with minimal monitoring research. And the long-term outcomes of this experiment on groundwater and climate change are unknown. And I started my career off in the late 60s studying radioactive waste disposal. And I got to know the nuclear industry well, and that they were funding my research for a decade or more. And I became an admirer of nuclear power. And so nuclear power and shale gas have two or more things in common. They're an amazing technologies in their own right, and they can produce lots of amounts of power, particularly electricity. They have in common the fact that science has gone totally off the rails. So the reason why we don't have deep disposal facilities for nuclear fuel is largely because the science has been so mind-bogglingly misstated by government and whatnot that there's no reason for the public to believe anything they're told on this topic, and that certainly is the case in Canada at this time. And we've written this here in an article. And then we followed it up with an article comparing shale gas development to the errors made by the nuclear community by misinforming the public on science and by not doing the right type of research at the right time, etc. So rapid development of shale gas has outpaced the science and the regulatory framework, and nobody debates this. I think there's a big agreement on that. And then in Canada, we've got politicians who will say anything. This is the second highest ranking politician in the province of British Columbia that really is desperate to get on with shale gas development. There's never been a leaky well in the province of British Columbia. And British Columbia has the most advanced regulations in the world. Having the most advanced regulations in the world really doesn't mean anything, since all the regulations are rather weak. Now, here's an interesting one. This is at least formed a little bit better. I don't see any place for fracking. The science simply isn't reliable enough. The technology isn't reliable enough, and there's too much danger to our water supply, to our environment in general. But the mayor of New York has no skin in the game, so his economy can be doing well because of shale gas imported from Pennsylvania. The mayor of New York is not saying that he's against shale gas development in Pennsylvania, just in the state of New York. And this gets at the much broader issue of ethical energy and all of that. So we have the province of New Brunswick, where the voters have voted out their government because the government was going to very gently tiptoe into shale gas development. But the budget of the province of British Columbia comes basically 40% in transfer payments. And the way we work in Canada, the poor provinces receive money from the federal government, and the federal government gets its money from taxing the rich provinces. And the only rich provinces we have now are Alberta and BC. So New Brunswick has the great luxury of turning down shale gas development while having 50% of all of their provincial budget money basically coming from Alberta. What does that mean? It basically means it's coming from the tar sands development. Interesting ethical conundrum. You turn down shale gas development, but basically your economy is supporting by tar sands. I wouldn't have any idea about whether or not the impacts of one versus the other are better or worse or anything. It's just this is the debate that's needed. So at the end of all of this, I wonder if expert panels do more harm than good in a case like this. And why is this a special case? It's a special case because expert panels were formed when basically there was no expertise. So it's really not an expert panel. These panels are panels of people who have long resumes that are asked to sit down in great haste and then try and figure out what's happening. And I think there must be a better way in our modern world to find out what's known scientifically about a topic than put a bunch of people in a room for 2 days, 5 times, who then are write a report and then get some of the things really wrong, like we did on seismicity. So at the end of the day, the world population outside of the US and outside of Western Canada is up in arms and very fearful about shale gas development. So much so that even in places of Europe where they'd much rather not buy Russian petroleum, they're going to forego fracking because of all the fears based around it. And you can say, well, are these people environmentalists? Are they kind of crazy? Are they overexcited? But at the end of the day, there's nobody who can speak to them in a rational way based on scientific evidence. So thank you for your attention, and please don't shoot me. I'm just a messenger.
Questions, please.
Yeah.
Can I ask a surface water question?
Probably, yeah, certainly. Probably won't get an answer, but
I hear from the internet that they're contaminating the surface water with the process fluids. They have wastewater treatment plants associated with this technology, and that they're discharging into the rivers and they're contaminating our rivers.
yep. So,
Is that true?
Well, in Canada, our regulations are that you can't store the flowback waters or any of these fracking fluids in pits. Everything has to be stored in tanks. So if you want to get rid of all the possibilities of spills and leakages and whatnot, you can do that by just spending more money and making sure that your storage process is better. So I gather, yeah, some pits have overflown and there's problems there because of lack of inspection, etc. But the flowback water is a really big deal, and the industry is increasingly doing more and more recycling. But at the end of the day, you end up, basically 50% or more of the water you pump down to do your fracking comes back up. And when it comes back up, it's got the natural chemicals, whatever that might be, whatever radioactivity and heavy metals and whatnot, and it's got the fracking chemicals. So the flowback water is basically a toxic liquid. And if you're in a part of the country where you can very conveniently get rid of that by deep well injection, as you can in Alberta and British Columbia, that's perfect. If you're in the Marcellus in Pennsylvania, where you have to ship it to Ohio, and then it just opens up a whole new world. So one of the reasons why getting fracking going in eastern Canada has an additional difficulty to it is handling the flowback water. And flowback water has been going to municipal sewage treatment plants and things like that, and they're not built to treat it and whatnot and so forth. So flowback water is a big deal, about which I don't know much, but it's a big deal. Yeah.
Are improvements being made in plugging wells that are abandoned?
So, it's not that the oil and gas industry can't plug wells that won't leak. You can't plug wells, as I understand it, with cement that won't leak. Well, you'd say, well, why does everybody use cement? Because if you use cement, everything's cost effective. Okay, and 20 or 30 years ago, Dow Chemical produced a chemical called Dowel Sealant. And it's chemical gel, and it's truly amazing. You put that in anything, and it seals it, and it continues to seal, and it doesn't degrade. And that sealant can be used for packers. So with more money, you can use better cement, and better cements are being used, and you can actually have packers in there. Now, until recently, and this apparently isn't the case in all states, you don't even have to seal the whole annulus. So these hundreds of thousands of wells that are across the continent, they don't even have cement in the first place pumped into all the zones, because it was cheaper just to pump a bit of cement here and a bit of cement there, etc. And if you don't know where the gas-rich beds are that you punctured, then you really don't know anything. So the first step is to require that the entire annulus be sealed. And the second step might be to use very sophisticated geophysical tools to see if you sealed it. The third step might be that you do a better type of pressure testing to see if you've sealed it, et cetera, et cetera. Now, I mean, as a taxpayer and whatnot, I guess what I'm concerned about this is what we don't want to see in Canada is basically hundreds of thousands of wells having to have millions and millions of dollars spent on them in the future to reseal them. And it's like a hernia operation in a way. To do a hernia operation, as I'm told, they're relatively easy to do and relatively inexpensive when you do it. But if you do it poorly and the operation hasn't been done properly, to fix a hernia operation then costs 10 or 20 times as much. So fixing a well that's gone bad is a real big deal. And I think the last time I gave this talk, I was in Denver, and a person came out of the audience, and he's in the business of fixing wells. And he told me about a well that he goes and visits in Canada where they spent $20 million trying to get a seal back in place. So, the well's leaking somewhere. The stuff is coming up. The gas is coming up. It's getting out in the environment because you can find it. And then the question is, okay, where's the leak? How are you going to plug it? So then you go down and you blast holes in your pipe and you squeeze cement in. And I mean, there's no program that we know of where there's any independent verification of all these new cements. So when you talk to the industry, and the people I know in the industry, they're trying to use the best cements that they can buy without going out of business. So there should be programs, and then it would need to be really government run in some way, that evaluates cements. Just like in the old days, there were programs to figure out how people would mine and whatnot, and do all the geomechanics so the mines wouldn't cave in and kill people. So just a comment in terms of ethical energy. So low-priced gas has caused nuclear plants to be shut down in the U.S. The nuclear industry was threatened by the Fukushima disaster, but it's really being killed by low-priced gas. I'm from the province of Ontario. 60% of our power is nuclear, 20% of our power is hydroelectric, and we have no coal burning, and a little bit of solar and wind, et cetera, et cetera. So we've had a very successful nuclear program, and we're not going to build any more reactors, and the reason being given is you just can't afford to build nuclear reactors if you can buy gas at the present price. But the environmental costs and all this monitoring we're talking about aren't built into the price. So we reached the crazy state in our humanity where we're shutting down nuclear plants, which in a climate change aspect, those plants have to be very positive, and they've worked and caused very few problems. We're shutting them down because we're buying low-priced shale gas that doesn't have hardly any of the externalities built into it. Yeah, there was a question over there before I started to ramble, I think. Yeah.
I noticed that in your prepared remarks, you said nothing about naturally occurring radioactive material, but you did mention it in your answer to the question. Is that, it seems to me that that's something we should be looking at, and I never see it in any of these presentations. Can you comment on that?
Oh, yeah. I mean, when you read the literature and whatnot, flowback water is a cocktail of all sorts of things. Heavy metals and radioactivity and, radium and whatnot and so forth. And so there are papers on that. It just kind of gets lost in the noise. But I mean, if you can't get rid of your flowback water by deep well injection, and you then have to deal with it with treatment, etc., okay, then you're faced with a very unusual treatment problem, because it varies from shale bed to shale bed. And people who are experts on shale beds, the geology of shale beds and the geochemistry of shale beds, they have very different signatures, very different origins. So the ability to make blanket recommendations and blanket regulations and whatnot, each shale bed is its own characteristic. And that gets to the business of the uncertainty in all these estimates. Apparently, Argentina has very vast shale gas reserves, and they've drilled more than 200 holes trying to figure out just how big is the reserve and how best to get it out. And then your flowback water can have a different chemistry, basically going short distances from one part of your province to another. So there's no end to the differences in the shale gas problem relative to conventional oil and gas development. Yeah.
My impression from your talk is that you feel as though subsurface migration of the fracking fluids themselves is well enough understood and controlled so that it's not nearly as big an issue as the unintended gas migration. Did I understand that?
That's right. I mean, as it's explained to me, and there are papers written on this, the hydrodynamics of the situation are it's highly improbable that fracking fluids will make their way up into the freshwater environment. And that's got to do with the pressure relationships and all of that. Now, that may not be the case 100 years from now when things repressurize and whatnot and so forth. Yeah, Phil.
So, related question. My understanding is we don't know where most of the water we put underground actually is going. Could you help me with that? Do we know?
That, I mean, oh boy. When I began to ask that question, like 50% and 80% or 20% comes back, and the numbers are very variable. Okay, well, where's the rest go? And that isn't known, as I understand it. And in fact, one of the first talks I went to had a representative from Halliburton, and he showed really neat, beautiful color graphs of all of their simulations as to what happens when they frack. Oh, I figured this is amazing. Hard to believe. Like, we groundwater people can hardly do that at 300 feet, and you can do that at 3,000 feet. And then I interviewed, professor at Stanford and one, and they said, that's just all. It's parametric modeling that helps them adjust their fracking operations, in a very parametric way, but it has nothing to do with the physics of the situation. So, I mean, like, that's the fundamental, volume balance, mass balance that hasn't been worked out.
So when we don't know where it all goes, how can we answer that we don't know that we'll have this water coming back later?
Well, the fracking chemicals, the flowback water comes back immediately, and then things get going. And the way it's explained to me that the pressure gradients are such that until the shale gas production is done, and the whole system has re-equilibrated. When we're in that era, then we don't have to worry about it. But then you say, well, what about the next era? Like the nuclear industry being asked to predict over the next 1,000 years, and we generally don't go beyond 30 or 40 years. So the questions about the long haul, they don't even get on the table.
Question up in the back?
You explained the issue with not being able to reproduce the science that
Yeah.
happens on people's land after
Yeah.
fracking exists. Do you think that's one of the main issues why science is so lacking, or what else is preventing any kind of decent science from being done?
Well, in Canada, science is being prevented because our federal government has decided that there are no scientific questions worth addressing. And we decided that on the tar sands long ago, too. So it's our national policy not to address these issues, as near as I can tell, and you may laugh, but there's no other explanation for it. Now you can say, well, okay, I have a little research grant with my colleagues. Well, that's amusement money. That's fun, and I get it through our National Research Council. And even the big project in Alberta, that's amusement money. The money that we need to spend to answer some of these questions is really in the many tens of millions of dollars a year in Canada as a starter. You'd say, whoa, wow, that'd be a national research effort. That's true, but look at the size of the business. Look at the questions. You know, so shale gas has been advertised and still is to be a transition to renewables. Okay, that's the pitch. Sounds good. You know, when I first read it, that sounded really good. It's cleaner than coal, but even people debate that. So if it's a transition to renewables, then Canada, we decided to get on with it. And the reason why the eastern provinces ban it is they don't have the money in their coffers in any way at all, even if they wanted to do the scale of research that we need. Alberta and BC do, but in fact that's a black box that's the political class doesn't want to open at this time. But it's interesting how the public feeling on this and whatnot, that science isn't on the table, which is a much broader affliction that our society now has. Shale gas development just kind of brings this science isn't on the table up into the spotlight, which is interesting. So to arrive at a consensus, as Dr. Oreskes indicates that we need to arrive at on whatever the issue is that we want science to inform policy, to get there you have to have a milieu of scientists. Because there have to be some people to actually form a consensus. And it means then that we have to have a whole new generation of grad students and postdocs working in this problem. And so one of the dangers of these expert panels with people with long resumes is we tend to, and by the time you got a long resume, you tend to think you know what you're talking about. And these panels don't have young people on them. They don't have all the people who come up with the ideas that cause new science to happen. Most of us have gotten pretty content with the paradigms we operate in. I've had a whole number of grad students write theses showing that I was wrong. And that's great. Yeah.
If there was to be the kind of science that you envision,
Yeah.
how long would that take to get to the
Yeah.
point where you say we could definitively go one way or the other, or understand?
So, to backtrack for a moment, by the time this expert panel thing had gotten near the end, and we're writing our report, I'm realizing we're missing probably the most important ingredient of all, the most important experts. And the most important experts would be those that could put shale gas environmental impacts in the context of something else. My own bias is I would take nuclear any day over shale gas and big hydroelectric projects. That's just my personal view. Is that based on anything? Well, not really, except living in a province where we have 60% nuclear and seeing the damage the big hydroelectric projects do to northern Canada and whatnot and so forth, and seeing the damage that's done with the Yangtze River Three Gorges Dam in China. there were people like me that would say, well, let's not fool around with all this fracking stuff. Why don't we just build more nuclear plants? Not the old type of plants, but the new type of plants that are generation, 4 and 5, et cetera. But to get back to your question, it seems that, a decade goes by pretty quickly. So if money were to be unleashed, then you have to get the right people to spend it. A PhD thesis takes 4 or 5 years, et cetera. So it's really easy to see 10 years going by before we'd have much of a scientific basis to actually have a discussion. And when I say that, people figure, that is, you scientists want to do science, and now you're telling me it's going to take a decade before you can say very much? Well, if you want to arrive at consensus, and look at the errors then in this seismicity thing. Everybody talking about, with great complacency that there's going to be no major, earthquakes above 3.5 or whatever ever, and then it happens. And then experts start to look at it, and you realize, whoa, maybe the next one's going to be 5.5 or whatever. Okay, we're traveling in a particular world here where the science is so crude, it's not clear that we can say anything. And as Phil mentioned, like, where does the water go? When you can't discuss that, like, what can you discuss? So what do we know then about fracking? We know that it's an amazing technology that actually gets you gas. We got lots of proof of that. And so it gets you gas, and the gas then production goes down to about 10% of what you get at your peak. And it goes down, and what's amazing, the graph almost levels off. And the fact that it levels off at 10% and not 1% means then you have a shale gas business. So when the gas starts to level off, then what are they going to do? Well, I'm told they're going to go back in and frack again. Because that's what we know how to do. Like, we've developed an amazing technology for getting gas.
Your field experiment in Western Canada envisions measuring both natural gas and CO2.
Yeah, it's going to be fun.
Can you comment a little bit about the similarities and differences between
Well,
CO2 and carbon storage systems?
Well, so that site was funded on the basis that it would be a CO2 storage experimental site. And we just converted it basically over the last 6 months to tell the government, no, it should be a CO2 and methane site. So basically, they weren't intended to be the same sites at all. And when you get right down to it, it's by far, I think, the methane experiments that'll be the most important at this time. And that project was originally envisioned by some excellent geophysicists, mostly interested in caprock. Okay. So caprock is this amazing rock that keeps things from going up and whatnot, and that's going to be interesting. And the shallow caprock is likely to be leaky, and that's going to be fun, and then the deeper one is likely not going to be leaky, et cetera, et cetera. So it'll be a playground. But it's actually got some old oil and gas wells on it. They're sitting there, abandoned. And it's got an active coal bed methane well on it. So wow, we find ourselves with a playground with actually an old oil industry wells and an active coal gas methane well at 700 meters. And we'll put in our own domestic well and we'll just kind of do stuff. And it's all going to be safe because it won't embarrass anybody, get anybody in trouble, because it's a playground, not the real thing. Yeah.
Would you be expecting methane to be coming up through potentially a natural fracture that's not being already going in the air over it with spectrometers and so on?
Oh yeah, methane's coming out of the ground. I mean, in some of these oil and gas rich areas, methane's coming out of the ground. So they're all such a new fancy equipment. And the British report recommended, which was brave on their part, they said not only do you have to measure the leakage at the wellhead, and so all these numbers that have to do with leakage at the wellhead, they're all biased low. Okay, so when the industry got excited about this, they funded the University of Texas to do a big study and sample all sorts of wellheads. And my attitude to that, well, that's only sampling at the wellhead. You're not looking at the soil. So it's got to be a complete package to be able to have a reasonable conversation. So in Quebec, it was interesting. We got going, and there were 29 wells that have been drilled, shale gas development, fracking wells in the province of Quebec before they banned it all. And then they went out and they measured the leakage in these wells. And depending upon your point of view, the one group would say, oh boy, they all leak, fair enough, but most of the leakages are really small. Like any leakage at all is a big deal, because you don't know where it's leaking into before it actually gets to the surface. And so the black box in all of this is basically what we're measuring in the way of leakage is bias low, and you got to go into the system and somehow figure out how to measure stuff. And that raises the question then, what permanent probes should be buried at each pad? Now, industry and with the support of government in Canada, their position is we want nothing at pads. We don't even want a monitoring well, because it opens up, well, if we're going to have one monitoring well, maybe we need a multi-level system. And if we don't know the direction of groundwater flow, maybe we need one on all four sides. And then do we need it all the way through the freshwater zone into the brackish water zone? And so it opens up a whole black box. And I've been viewed as kind of a threat on this front. And people say, oh, Cherry wants every pad under the sun being monitored with all these devices. And that's not what I'm advocating. I'm advocating, let's take a few and monitor the hell out of them and use every type of instruments we can imagine and see what we learn.
Anybody else?
Yep.
What has the government of Canada done with your report?
Next question?
Well, so there's a story there. So it was my understanding that when the panel finished its work, that nobody could change the wording in any substantial way at all. And I had a lot of troubles with this little bureaucracy in Ottawa that runs this affair. They're not a reputable group like your NRC and whatnot. And so and so the agreement was if they changed, because they're going to edit it, fair enough. They're going to put it to an editor. And the deal was you can change no sentences of substance unless I see them. And they changed a bunch of them. But the trivial ones, they ran by me. The non-trivial ones, they didn't, except for one sentence. And the last sentence of the report said, whether or not shale gas development in Canada is going to be positive or negative in the long haul will depend upon how society views the technology and how government manages it. And they took out how government manages it. Can you imagine? So this is a war that I'm having. On another front, and I've written a report on that, and the media has reported on it a little bit, but I haven't really taken it all the way down the road. So that was a form of censorship that should, it's mind-boggling that would happen. But that's the nature of science and technology and politics in our capital at the moment. No federal government scientist in Canada is allowed to talk to anybody on their science that they're doing on any aspect of it that might have to do with policy. It all has to be vetted through basically the policy office. Like, what science can you do that has to do with the environment that doesn't have something to do with policy? So I have a friend who's been with the federal government for many, many decades, and every time he leaves on a trip to go to his conference, his wife says, well, are you going to be fired on this trip? His answer is he's near retirement and he doesn't care.
What's happening in the state of Maryland? I noticed that, and listed at the bottom, are they by any chance doing it in a different way?
I don't know. I just listed that there because one of the people I know, Don Sauter at US DOE, is on a Maryland committee, and so I really don't know what's happening there. Now, I should point out that the Quebec government, I think, did things right. They spent a lot of money on marshaling the scientific community to learn everything you could learn without fracking itself. And they wrote a big, long report that they haven't translated into English, so we can't quite read it. But I'm told about it, and I've spoken to people who have been on their panel. Okay, and at the end of the day, then they banned it. They banned it, but in fact, they're busy doing research and whatnot because they know that someday it may make sense to have shale gas develop in the province of Quebec. And that goes to this whole issue of ethical energy and whatnot. You know, we can't be against shale gas development. We have to decide what we're going to have as our energy mix. And shale gas development may make sense in Alberta and BC. It may not make sense in the eastern provinces. It may only make sense in areas where you can deep well inject the waste fluids. Maybe that's the only place that makes sense, etc. Yeah.
I'm wondering if you see the possibility of certain elements of industry seeking competitive advantage by doing their own research and coming up with a safer program. It doesn't seem that government wants to invest in it. But could there be a marketing advantage to an industry that came up with a better set of practices that could pass the scrutiny that you're asking?
So I'm getting out of my league here, but so fracking got going with little companies who could push the edge of technology and who weren't burdened by bureaucracy. Okay, and when the big four, the big five, Exxon and Chevron, realized that there was a game going on that they weren't part of, they bought their way into it. So the current CEO of Exxon, you know, staked part of his career on a $40 billion purchase, I think, of a company called XLT. And I met one of the guys from XLT at a shale gas conference that I organized, and he was there with Exxon. And he said he left Exxon because he wanted to leave the bureaucracy long ago and started XLT. And then he and his colleagues sold it for $40 billion, and now he's back with Exxon. The point being here that the shale gas development now has large companies that want to be in business forever. And they would, I think, in my conversations with them, they would much prefer higher demands, higher regulations, more inspection, larger penalties. So the problem is basically you've got the big players that are going to be around forever who operate according to certain environmental ethics and whatnot. And then you got the little guys who aren't going to be around next year. And so basically it's still a free-for-all. And if governments won't raise the plateau then in terms of inspection and regulation and penalties, so that in fact you have to be big to play, and not like the mining industry now, you can't just go out and start a mine. There are only about 10 big mining companies left in the world, and they do all the world's mining. The little guys explore, they do the prospecting, but the big companies build the mines. And that's because they can play at a higher level. So it's government that's, and in no way am I criticizing industry here, it's government not doing their duty. And government says, well, we can't raise the regulations because the price of gas is down. Well, the price of gas is down because nothing's built in, etc. So it's kind of crazy. Government's actually doing themselves in by not being willing to raise the playing field. So there's no rigorous groundwater monitoring going on at any fracking pad on the continent. And there was a project that was going to start, spearheaded by DOE. It was going to start last month, but it got canceled for lack of funding. And the originators of that project had found a company that would allow them to do research at their pad. And the site's on state land in Pennsylvania, a perfect research site. And so why would the company allow that? They're so small, they just didn't care. It just seemed to make sense to them. Why wouldn't you have research going on at a fracking pad?
One or two more questions?
Yeah.
You might have just answered my question, but I was going to, you're demanding more research, which of course is great. Aren't we starting that at this test site in Pennsylvania, which I believe the research has been going on for a few years, USGS and DOE and Western Pennsylvania?
No, there's no pad in Pennsylvania that's actually being monitored. Oh, no. The critical thing is that you monitor before you start fracking. So the ultimate experiment is you're gonna build a pad, and for 2 or 3 years you monitor it. So you know it's all about background methane. Like methane is everywhere. So we gotta have to understand natural methane, and that's why we need baseline. So the only baseline monitoring that goes on is sampling domestic wells. That's not baseline scientific monitoring. So there still isn't a pad that has baseline monitoring going on, so that you can then track it into the future.
So at that test site, did that actually start program research start after the fracking?
No, the project I'm mentioning was going to start 2 years or 3 years before building the pad. We had it all designed, and we're about to start drilling and at least, getting things in the ground. And we know so little about methane in fractured sedimentary rock that there's a whole science to unfold there. Furthermore, in the last 15 years of my career, I've been focusing on basically the hydrogeology of fractured sedimentary rock with colleagues that I work with who know more about it than me. And it's one of the last frontiers then in physical hydrogeology. So when you look at all the textbooks and whatnot and you look up fractured rock, you'll find the compulsory 2 pages that the authors had to write, whether it's Friesenshire or whatever, where we sat down and we said, we can't write a chapter on fractured rock because we don't know enough. So we'll write 2 pages and we'll put in the cubic law. So we as a profession, really, it's a frontier. Just the hydrogeology of fractured sedimentary rock is a frontier. And then you add to it methane. It'd be a lot different if we're just starting off with sand and gravel adding methane. At least we understand the processes and the dispersion and all that stuff. So the only industry that has been studied fractured sedimentary rock is the nuclear industry, because like 50 years ago, most countries of the world decided that they would build their geological repository for spent fuel in granite. Okay, and the only countries that didn't decide to use granite was the US, because you chose Yucca Mountain long ago for political reasons. Germany chose salt. The Swedes and the Finns only had granite, and everybody else chose granite because somebody thought granite didn't have fractures below 500 feet. A crazy idea. And so billions of dollars have been spent. We did it in Canada, and I was on a committee years ago trying to find out, who decided that? Because we haven't been able to find any granite in Canada that doesn't have fractures all over the place. Nobody knows who decided it, but it was probably a public relations person. I think somebody asked a question, I got off track.
We have one more question.
Yeah.
So you mentioned there's very little we know about fracking, but one of the things we do know is we shoddily input the cement into the annulus. So that's one very concrete thing that we know.
Yeah.
Could you comment on the regulatory landscape regarding that in particular?
Oh, I can't. It's not as if an inspector is out there. You build a house, you have to have an inspector, visit every week and whatnot, but you can have a whole fracking pad and not have an inspector stop by. So in fact, it's pretty well up to the companies how good a job they want to do. And some of the big companies really want to do as good a job as possible. So I'm not in any way suggesting that shoddy practice is the norm. As Dick Jackson pointed out, it's an extremely difficult challenge. And we have no idea how small these annuluses have to be in order to be trivial. So we don't even know what the technical challenge is. So it's not a matter of shoddiness. It's a matter of even when you recognize you have the problem, figuring out how to do it right is a big technical challenge. And the people I know in the oil and gas industry, each of these companies has their favorite cement. They don't want to end up in the future going around fixing a whole bunch of wells. That'd be a financial disaster. I gather there was a debate going on today about divestiture and whatnot. Interesting. What are the liabilities going to be in the future? In Canada, where we've mined all across our north, what we, the Canadian taxpayer, have been left with are basically thousands of little mines dotted across the north with mine tailings that are active. Okay, the taxpayer picks that up. Those companies are long gone. But the big mining companies now, everything is on them then to do a better job because they're going to be around for a while. So it's interesting, in one sense, we don't want a monopoly of industry. The mining industry now has 5 big mining companies and maybe 5 others, and it's getting pretty close to monopoly. But unless you're paying at the highest level, you can't afford, in general, then to do a lot of these things. So there's a level playing field now in the mining industry, more or less. You'll read all sorts of things coming out of Chile and whatnot, but at least on this continent.